Okay, so full laws of probability here, bringing together probability chapter 5 from year 1 and this chapter 2 and what we've seen so far. So if things are independent, that means that the probability of one is not affected by the other. Okay, and as we saw in year 1, the way to find that out is to multiply them together. Okay, there's often a question where you've been told this one here, and maybe you can get these from the diagram, and you have to check if it works. And if it works, they're independent. If not, they are not independent. How about the probability of A given B? Well, let's just go back to our definition. If they're independent, what we do is we say that one does not affect the other. So given B doesn't do anything, it doesn't mean anything here. The probability of A given B is just the probability of A if things are independent, because the definition is that the probabilities do not affect each other. Okay, that's independent. Another key phrase we looked at is when things are mutually exclusive. If they are mutually exclusive, easiest way to describe it, I would say, is like a Venn diagram where there's no overlap. So, what's the probability of these both happening at the same time? A intersection B. Well, it's zero because there's no overlap. So, that's all it is. How about the probability of A union B? Well, you might remember this is a bit like or, it's a bit like when you shade them. Well, clearly it's just the probability of A plus the probability of B. Okay. How about the general case? Well, we saw this one here from our formula. If you remember, we looked at a tree diagram and we looked at the probability of B, and then we looked at this one here, and this was the probability of A intersection B at the end. And the way we did it is we did the probability of B multiplied by the probability of A, because we wanted A here, given B. And with the tree diagram, you multiply the branches. So probability of B multiplied by this one equals that one there. And you can rearrange that. But this is actually written like this in the formula booklet. Okay. So I don't really get too concerned with remembering this. As you saw in the previous section, I generally just draw a Venn diagram and solve it diagrammatically. But the formula is always there for you to rearrange if you need to. And in general, what about A union B? Well, if we talk about the general case, we don't know if the, things look like this, for example. They might look like this. So if you were trying to find A union B, well, if you shaded A and then you shaded B, do you see you have a problem, which is you double count the bit in the middle. So in general, we say it's the probability of A plus the probability of B, take away the overlap, because otherwise this part in the middle, we want to avoid counting this twice. Okay. If they are mutually exclusive, by the way, that overlap area there would be zero. So do you see that this one also fits this case here as well? Okay, so these are our full laws of probability. And now we're just going to put them into practice. So explain what you understand by sample space. So a sample space shows all of the possible outcomes that can happen. You've seen sample spaces in a number of different ways. You might have seen them in a table. You've seen them in a Venn diagram here. What do we mean exactly by an event? Okay, so event is a set of one or more outcomes. So an event could be something like heads then tails, couldn't it? Because you might have like a probability attached to it. So that's an event. An event is a combination of outcomes. So outcome is the most basic level. Event is building up from that. Events A and B are independent. Well, as soon as I hear that one there, I think about this one here. Okay, this is my instinct is independent questions tend to be something to do with that top line there. So find A and B. Well, when they're independent, you just multiply them together. You multiply A by B, so a third times a quarter. What about A given B? Well, if they're independent, A is unaffected by B, so it's still just a third. A trick question, really. How about A union B? Well, we have to assume that it doesn't say anything about mutually exclusive or not, but we have to assume that they overlap. So we'll do probability of A. That's probability of A. Plus the probability of B. That's the probability of B. And what's the problem is we've double counted the middle part. So we'll do probability of A plus the probability of B. And because we don't want to count it twice, we're going to have to remove one lot of the intersection. Okay. Um, and then we get our answer. So it's sort of about like find out the different parts, use the parts, plug them in, etc. You've got some further examples here. So C and D are events such that this is C, this is D, C given D is this, and we've got to find out all these different things. So whenever I get given this one here, my instinct again tells me that I'm going to use, where are we? That I'm going to use this one here. Now, of course, the letters have changed. So what do we have? We have C given D. So that's going to be a C, that's going to be a D. D is taking the place of that one. Okay, and that is C, and that is D. And that one there is probably going to be quite useful for us. So probability of, where were we? Probability of C given D, we said was equal to probability of intersection C and D. Let's just go back because we can just use this one here. There's no need to get confused. The probability of D. So you can go back to the tree diagram, but it's not really necessary. Can we find C intersection D? Well, that one's there. We know this one. We know this one. We can multiply those together then, can't we? How about D intersection C? Well, you're just changing the positions. So you could just rewrite it. So D given C equals, well, intersection, it's not going to make any difference. So you could just use the same intersection. You could just write it the same way. You could just change that one, though, to C. And again, just confirm you do have all those numbers there to start with. Okay. Right. What's the last one here? So union. So how do we find union? Well, union, we find C, and then we add D, and then we take away the one of the overlap. And that's what's been done here. So hopefully that follows quite nicely. Again, we've got another example here. So state in words the relationship between two events R and S when the intersection is 0. So what does it mean when there's no intersection between them? So it means they're mutually exclusive. The events A and B are independent. You know where we're going to go with this. This is the probability of A. This is union. So find the probability of B. Well, A and B, it's not about R and S anymore. That's not important by the look of it. It's about A and B. So A is a quarter. A union B means all of what's inside the circles. We have to assume that they will overlap. A is a quarter. Okay, so how am I going to find probability of B when I've been given this part here? That's the question. Well, if I did 2/3 minus a quarter, that would leave me with everything inside this circle, wouldn't it? So I could do 2/3 minus a quarter to get that one there. Also, if they're independent, what does that mean? Well, it means that probability of A times probability of B is going to be equal to that intersection, probability of A intersection B. So what am I coming up with here? Well, I'm coming up really with two sets of equations, aren't I? I'm going to be able to find probability of only B with this part here. And I should be able to come up with some sort of equation using the fact that A multiplied by B gives A intersection B as well. So let's take a look at what we've done then. So we could say that 2/3, so 2/3 is everything inside the circles. So everything inside the circles is made up of the A circle plus the B circle and then minus the overlap. Because if you do the A circle, that includes the intersection. If you do the B circle, that includes the intersection as well. So you need to remove it once. So that's the first situation that we talked about. Then what are we using? Well, over here, we're using the independence. So like this is a difficult question, right? That's why it's 4 marks. So we've got 2/3 equals a quarter. So we're just copying that one from before. Plus probability of B and then minus. So they're saying what the intersection is here. So what is the intersection? The intersection is if they're independent, is the probability of A multiplied by the probability of B. And we know that one. We know that that one is a quarter. So what's all this about? Well, now you've reduced it. Okay, there are things you don't know, but you've reduced it to the same thing that you don't know twice. So you're able to put that into equation and find the probability of B. So that is not a trivial question. That's a bit difficult, that one. Especially to try and fit in a space like this. But if you reason through it and you think, the word independence probably there for a reason, and I would build a Venn diagram to sort of get an idea of what's happening, it can be done. Okay, it can be done. Then once you have this information, well, you're able to have a good go at the whole question, aren't you? Because you know what A should add up to, you know what B should add up to, okay, you know what it should add up to together, so you should be able to find out whatever you need to about this case here. So what's the probability that it's not A and it's B? Well, I think we found that out before. That's just 2/3 minus a quarter, isn't it? Let's have a think about that. So it's not A and it's also B. That should just be the same as 2/3 minus a quarter. Let's just check. So 5/12. Yeah, that's the easiest way to do that one. Yeah, I wouldn't do that. I would to be honest, C is easier to answer than B. So I would just do 2/3 minus 1/4. And then what have we got? We've got the probability of not B given A. Well, this is a trick as well, isn't it? Because they're independent. So this is just going to be the same as not the probability of B. B is 5/9, so I'm expecting 4/9 here. Okay, so that's a trick question. Again, you don't need to do all of this. You know that they're independent, so the probability of B and not B given A doesn't mean anything. The A is meaningless because it's an independent event. We talked about that. So you're just finding, you could just think of this as find the probability of not B. And you know 5/9, so this should be 4/9. So don't be put off by the fact that sometimes what they do in the mark scheme is quite different. Sometimes there's an easier way of doing it. Pause the video then, have a go at those ones there, and I'll reveal those on the screen. So assuming you've done that, make sure you've used the information here. So what do we have? A and B are mutually exclusive. In other words, the A and the B circle shouldn't overlap. We have to expect, because it doesn't say anything about mutual exclusivity between A and C and B, we have to assume that there will be some overlap. So that's how we would draw it, with some space on the outside. We've got some probabilities here. We've got A and we've got B. So A given C. A given C, well, they're independent again. So that's the trick question again, isn't it? Yeah. A union B. So because they don't overlap, you can just add them together. If you say, what about taking away the overlap? Well, there is no overlap, so there's nothing to subtract. You're subtracting 0. And the probability of C is going to be some problem solving based around that, 5/8. Okay. Just a final note is given here that conditional probability often uses, well, pretty much always uses the phrase given that. So when you see given that, so for example, this one here, if you see given that, it makes up this part of your conditional probability. So given that Bob walks to school, so B is about walking to school. Find the probability that he is not late. So this is about sort of the late or not late thing. Okay. So yeah, A not late they're using here. So given talks about the second part of your probability. If you see independent, you need to be very, very mindful of that. Okay, so remember that intersection is when you multiply the component parts. And conditional probability doesn't, if you're talking about conditional probability between two independent events, it doesn't affect anything at all. Okay, so that is the same as that. Okay, and that takes you up to 2D. So I'll just display those rules that we looked at one more time. This is what you need to get fluent with using.